All right, so in the previous lesson, we spoke about the ability to represent binary data in registers with switches, and then I also spoke about some kind of circuit that you could pass these two the data in these registers through, and it would add them up. And now we're going to talk about how complex it actually is to accomplish that. So to get started off, we're gonna speak about one of the most fundamental electrical components, and the earliest of computers were built with these. They're really not a good choice because they've got moving parts. But for explaining how this works, it's because they got moving parts that makes them great. So let's talk about the relay. Okay, so this is an electrical component, and at the heart of this is this electromagnetic coil. So basically, it's a piece of metal. It's a little piece of metal. It's got a coil around it, and when there's no current flowing around that coil, there's no magnetic field either. But if a current flows, then a magnetic field is induced in this piece of metal, and the field is these like teal green lines over here. That's invisible, obviously, unless you have iron filings. What this magnetic field does is it pulls this little lever down. It's a spring-loaded switch. When it's off, the switch is in this position, and so if there was a voltage flowing through this wire here, it wouldn't go anywhere. So if in this case, if there's no voltage coming in, there's also no voltage going out. And when there's the voltage is switched on, the lever's pulled down, the circuit is closed, and the voltage flows out. So wiring up a relay this way means if it's on coming in, it's on going out, and if it's off coming in, it's off going out. And that might seem obvious, but there's a different way we could wire up a relay. The other option that's available is to wire it like this, where now the voltage can flow when the relay is off. So in this case, you're getting the opposite effect. When the input is off, the output is on, and when the input goes on, pulls the lever down, the circuit is broken, and so the output is off. This is known as a NOT circuit because whatever goes in, not that comes out. And this is one of the three fundamental circuits that you'll need to understand about. And so let's talk about a truth table. What a truth table is it just tells you what these circuits are. It's a gate. We could call it a gate or circuits, and there's a difference, but you'll understand the difference as you study more. So a NOT gate, if the in is off, then the out is on, and if the in is on, then the out is off. Okay, and there's a symbol for a NOT gate that you should recognize, that you should know. So it's this triangle, and always take note of the circle. The other thing you should note with a NOT gate is it's only got one input and one output, which makes sense if you scroll back up here because there's only one going in and one going out. Of course, there's a voltage that needs to be supplied. Okay, so let's have a look at it. So there's three primary circuits. We've spoken about the NOT. Let's talk about the AND. The AND circuit has two inputs and one output. And why they call it AND is because both input 1 and input 2 need to be on before the output is on. And let's see how this works. So in this case, obviously, if there's a voltage coming here, it can't go anywhere because the circuit's broken. But if the first input is on, the voltage could now technically flow through here down this wire, but over here again it can't get through. And if this one was off and this one was on, well, the voltage never gets through this first step, so it can't flow through the circuit. But if both of them are on, now the voltage can flow through there, and it can exit. So an AND gate requires both of the inputs to be on before the output is on. Let's have a look at an AND gate's truth table quickly. So if the input 1 is off and input 2 is off, then the output's off. If one is on, but the other one's off, we still got an output of 0. And if the one is off, but the other one's on, the output's still 0. But when both of them are on, then the output's 1. And this is the symbol for an AND gate. It's just this kind of rounded, like straight bit for there, and then a rounded edge. And a straight back. Take note of the straight back. And obviously this one's got 2 inputs and 1 output, which is different to the NOT gate. Okay, so the third of the primary circuits is called an OR gate, and they call it an OR gate because whereas the other one had to be both inputs, this one and this one only needs to be one of the inputs, so this one or this one. So that's why they call it an OR gate. So let's test it out. So the voltage is broken here, but if you switch it on, the voltage is on and it can flow. Over here, the voltage comes in here too, so if this one's on, it can flow. So whichever one is on, it will flow, and if they're both on, it will still stay on. So that's how an OR gate works, and we can see its truth table. If the 2 inputs are off, then the output is off, but if either one is on, then the output is on, and if they're both on, the output's still on. This is what an OR circuit symbol looks like. It's where the AND was round, this one goes to a point, but because when you're drawing it, it's not always that obvious, they've made it more clear by giving it a rounded back like this. And obviously it has 2 inputs and 1 output. Okay, so those are the 3 fundamentals, but you can mix those up to create some more interesting circuits. And we'll get to the reason why we're talking about this, but just bear with me for another minute or two. So what we can do is we could mix an AND gate and a NOT gate. So now what I've done here is what you're going to get in computer science a lot. This is called abstraction. So you could be sure that all the circuitry that I've showed you is inside of this AND gate and works the way as I've showed, and the same is true for this NOT gate. But I don't need to show all the complexity. We can zoom out a layer, and that's called a layer of abstraction. So this gate is called the NAND gate, and it's really just a combination of 2 of the primary gates. So we've got our AND, and then we've got a NOT. And as you can see here, because both inputs are off, and so the AND's output is off, but a NOT will always inverse the current, so it's giving a value. So okay, so 0 in, 0 in. So this is a truth table here. You can see our truth table. If the output is 1, if the 2 inputs are 0. The switch 1 on, well, we see our AND still isn't activated because it's only 1. So this is our truth table for 1 on, and if we switch the other one on, obviously it's the same thing because it's an AND gate. But if we switch both on, now we're getting the first time that we got an output that's off, is only if both inputs are on. So let's look at the truth table for a NAND gate. So if the 2 inputs are off, then the output is on. In fact, as we said, the output will always stay on unless both inputs are on. Okay, NAND gate. So next, a NAND gate is quite easy to understand now. Remember that the NOT gate had the circle. It was a triangle with a circle, and the AND gate is a round one. So this circle always depicts that NOT, like that it flips the value around. It inverts the current coming in. And this is an AND gate. So it's quite easy to understand that this is an AND gate. All right, so now the XOR gates is where things start getting quite interesting. Again, I've come up 1 layer, zoomed out 1 layer, so you don't need to see the NAND gate is 2 smaller gates. We've just put it in its own box. So we've got a NAND gate, we've got an OR gate, and we've got an AND gate. And this is a very interesting circuit, and you're going to see why now. Have a look at these inputs and see what is interesting to you about this, bearing in mind what we spoke about in the first episode about binary addition. So at this point, we've got inputs, both inputs are 0, and the output is therefore 0. And you can see here there's some current flowing. Because it's a NAND gate, remember how a NAND gate works, because there's no inputs going through there, it's inversing it, and so the current is flowing, but this is an AND gate, so it's not passing through. Okay, so what if we had to have 1 input go live? Okay, so here's input A is high, so we've got 1 there, and it's going into this NAND gate, which isn't flipping this value because it needs both of these before that happens. But it's going into this OR gate, and an OR gate only needs 1. So the OR gate is closing this AND circuit, so now we've got an input. So 1, 0, 1. Okay, so let's switch that one off again and try the other one and see what happens. Well, this one also sends the outputs to be high, because when it comes in here, the OR gate is activated, and even though there is one input in the NAND gates, you need two to switch this over. So still we've got the AND live, and we've got the AND getting used, and then we've got the outputs. So 0, 1, 1. But if we put both of them on, this is the first time now that the NAND gate goes off, and so the AND gate is closed. And so with both of these on, we have got the output as 0. So this is where it gets interesting. If you can remember how to do the binary addition that we spoke about in the previous lesson, we would have 0 plus 0 would equal 0, 1 plus 0 would equal 1, 0 plus 1 would equal 1, and 1 plus 1 would equal 0 with a carry. So this exclusive OR gate, or an XOR gate as they call it, is almost doing addition. We just need to find a way to have that carry bit taken care of, and then we found a way to make our computer do addition. So let's have a look quickly at the XOR's truth table. It's exactly like we spoke. It looks almost like binary addition, just we're looking at it sideways this time. 0 plus 0 is 0. We've already spoken about it. Everything's good. You can double check it if you want. And this is an XOR gate's symbol. So it's an OR. That's just an OR, but it's got this lines, like curved line in front of it to express that the OR has got an exclusive output. Okay, so now let's have a look at what we can do with these exclusive OR gates, and we've finally been able to finish off the whole process. So we've got I've zoomed out a layer again, another layer of abstraction. So the exclusive OR gates, which remember are made up of a bunch of little OR gates now, and circuits. So there's a lot of circuitry going on in this little block here. So, but we've zoomed out and we've put it in its own box. So we've got 2 exclusive OR gates, and if you want to check the truth tables to make sure that this thing is working, you can. We've got 2 ANDs over here and an OR, and this was a circuit that somebody had to figure out. And then over here, we've got 2 inputs, like we always have, but now we've got a third one. We've got a carry in. And we've also got a carry out and an output, like we always have. So let's see. This is supposed to do a full addition. So let's see if it does. So 0 plus 0, 0. It's working so far. 1 plus 0 gives you 1. And here you can see it. 1 in, 0 in, and your 1 out with no carry. And if you wanted to follow this, you could check that all the numbers are working. They're good. So that one works. Let's switch that one off and switch that one on. And it works as well, because 0 plus 1 should also output 1 with no carries. Okay, so if both of them are on, what are we going to get? Okay, so this time we're going to get output of 0, which is right, because we want 1 plus 1 to output 0. But if you look here, the interesting thing about this one is now we've got a carry out that's live. Okay, so what does a carry out mean? Well, it means if you had another one of these sitting next door to this, you could take the wire from this carry out, wire it around into here. And so let's say the next one on the other side was 0 plus 0, but it's got a carry in from the other one's carry out. We're going to get this. 0 plus 0 with a carry in gives us an output of 1, which is right. So let's test it all the way. If we had a carry but a 0 and a 1, or a 1 and a 0, well, then we're going to get a carry plus 1 is still going to give us 0 with a carry, so that's right. But what if we got a carry and we're doing 1 plus 1? Well, then we get 3, which is 11, which is 1, and the carry out. So this full adder circuit had finally completed what they needed to do. This truth table does an addition with a carry, which is exactly what needed to be accomplished. So let's just have a quick look at this. So over here is this here is one of those adder circuits. So they would have 8 registers, 2 of them in a row and 8 outputs. And then in between this is that full adder circuit that we just spoke. And you could check that each one of these would work. So 2 zeros would come in and you'd have a 0 output. Then it carries on and you could follow it through, and it flows down like this, where the carry, if the carry is out is low, the carry in is low. And then you get a 0, you get a 1. So we got 1 coming out, but in this case we'll have no carry out, and so we'll have no carry in. Now we got 1 and 1 coming in with 0 carry, which will now give us, what do you think it will give us? That's right, it will give us a 0 with a 1 as a carry. So it carries out, carries in. Now we've got 0 in, but we've also got a 1 in. So the 1 and the carry will give us a 0 and another carry out, which gives us a carry in on the next one. So 0 plus the 1 carry in. Oopsie, it's 0 plus the 1 carry in gives us 1, yeah, and no carry out. And now there's zeros all the way to the end of the register. And if you had to check that number, if you had to add these two up, you would notice that that register has done an addition. Okay, so can you see how complicated it is? The previous lesson we said, okay, so let's just have numbers in these two registers and we add them up using this circuit without ever considering how complicated it is to make a circuit that can do that addition. Okay, so we want to make a computer as simple as possible. When you're adding complicated circuitries, you don't want to, you're going to have problems. So now they wanted to move on. Okay, we can do addition. We figured out how to do that. Or let's do subtraction next. That's the obvious next step. And then the guys working on the hardware said, well, wait a minute. We don't need to figure out a new circuit to do addition, because if you want to do subtraction, you just got to add a negative number. So saying, like, if you wanted to say 3 minus 2, you don't need to make a circuit that does minus. You could just say 3 plus negative 2. And that's the first time everybody thought, hey, wait a minute. How do we represent negative numbers in a system of on and off switches? We're going to cover that in the next lesson.